Hi everyone, my name is Zhou Shuhua and our paper is Efficient Angiography Simulation for Complex Vessels. Endovascular intervention is an effective therapy to treat cardiovascular diseases, which is the #1 cause of death globally. Endovascular intervention has high requirements for doctors' manipulation. However, due to limited training resources and the complexity of the procedure, training of angiography and endovascular interventions is a big challenge in general. Interactive virtual simulator has become an alternative for medical training. With computer-based simulators, students can practice some basic skills repeatedly with multiple medical cases and computerized objective assessments. However, the simulation realism that how well the simulation results can closely represent the real-life cases remains a big challenge. Among them, angiography simulation is crucial to improve the reality of virtual surgery. Only accurate and real-time angiography can help doctors identify vascular lesions and provide correct guidance for doctors' operations. Despite years of progress in contrast media simulation, there are still three main obstacles in practice. First of all, the flow simulation in blood vessels should correspond to the actual situations as possible without penetration and have good robustness for complex human blood vessels with different radii and curvatures. Secondly, the diffusion of the injected contrast media will be affected by blood flow, so it is infeasible to consider the contrast media diffusion in isolation. Finally, the angiography process is displayed on the monitor in real time, so the algorithm should guarantee real time, which has a high requirement for algorithm efficiency. To solve these problems, we proposed a method based on implicit boundary representation for angiography simulation. Given the complex and irregular characteristics of the vascular boundary, we used the sign distance fields to represent the vascular boundary and used the Gauss-Cronrod quadrature to compute the boundary domain intersects with the particle support domain accurately. We pre-compute boundary volume of the intersection area to reduce the real-time computational cost, and generate a volume map to store the values and to query them in real-time simulation. Once generated, the boundary volume map can be reused in the subsequent simulation without regenerating for every simulation, which greatly saves time and memory for initialization. In addition, we improve the multiple fluid model by taking the vascular viscosity into account, which achieves more realistic and accurate results. The left hand is the framework of our algorithm. As depicted in this figure, our algorithm consists of two parts, the vascular boundary volume map and the multi-fluid mixture model. When the simulation starts, we initialize the particles and the simulation parameters. Then we generated a corresponding vascular boundary volume map, and if the volume map was existed, we load it directly. In the multi-fluid mixture model part, we query the volume map in the real time and use the queried value to compute the dynamic by mixture model. Finally, we update the velocity and position of the fluid particles to realize the propagation of the contrast media. Our pipeline, as shown in the right, consists of CPU and GPU parts. In the CPU part, we initialize the particle states and simulation parameters and generate or load the volume map of the vascular boundary. The GPU part performs the simulation loop and undertakes the primary mathematical calculations. We parallelly conduct neighbor searching and boundary volume querying for each particle. Based on that, we can update the volume fraction, velocity, and position of each phase of the particles, and thus simulate the contrast media diffusion in blood. Our method is essentially a SPH-based method which simulates fluids as discrete particles. In basic SPH model, the density of a particle can be given by the weighted sums of its neighbor particles using a Gauss smooth kernel. And in our method, each of the particle is a mixture particle, which carries the properties from two phases. One is contrast media and another is blood. We use mixture particles to describe the coupling of blood and contrast media. The distribution of blood and contrast media is represented by their volume fractions rather than checking fluid interface. So first, we have mixture properties of the mixture particles, such as mixture velocity, mixture density, mixture pressure, etc. And we also have the volume fraction of phase K. Here, alpha 1 is the volume fraction of blood, and alpha 2 is contrast media, and the sum of them is 1. We also have the phase velocity UK and the drift velocity UMK, which denotes the velocity of phase K relative to the mixture mass center. Here is the governing equation of our simulation. The left side of the first equation is the substantial derivative of the volume fraction of phase K about the mixture velocity UM. And the left side of the second equation is the substantial derivative of mixture velocity UM. Therefore, we can solve these two equations by calculating the time integral on the right side to update the volume fraction of phase K and the mixture velocity, and thus simulating the contrast media propagation in blood vessels. When the particle is located at the boundary, as shown in this figure, we can extend the particle support domain to the boundary. At this point, the integral density domain of the fluid particle can be divided into the fluid domain and the boundary domain. For fluid domain, density can be calculated by the weighted sum of its neighbor particles. And for boundary part, the continuous density contribution of the boundary region can be defined as this equation. And VB is the volume of the intersection area between the particle support domain and the boundary. In our method, we represent the vascular structure by sign distance function, who converts three-dimensional space into one and represents the boundary by zero isosurface. The sign distance value of any point in a finite space is equal to its minimum distance to the boundary, and the value is negative within the boundary while positive in the fluid domain. Based on that, the boundary volume VB can be calculated by this equation. It can be seen that the computation of the equation is very complex and expensive, which requires not only numerical integration, but also the sign distance value of the particles. To improve computational efficiency without sacrificing accuracy, we pre-compute the intersection boundary volume to generate a boundary volume map. When the simulation runs, we query the boundary volume map in real time and use the queried value in the mathematical calculation of fluid particles. Finally, we conduct several experiments to verify the effectiveness of our method. As human blood vessels are very complex, but essentially belongs to stenosis or bifurcation types. Therefore, we designed a simplified stenosis model and a Y bifurcation model for experiments. We render the values to images, including a render image to simulate the angiography results, and images of velocity and pressure, which visualize all particles' pressure and velocity values to give a more intuitive view of the particle state. A2E shows the overall process after contrast media injected to stenosis vessels. As shown in the color band, blue to red represents the increasing values. We can observe that the particle pressure near the boundary was not significantly different, and the particle velocity near the boundary was low due to the effect of boundary viscosity. Moreover, the color on the left side was slightly yellow, suggesting the pressure on the left side is larger than the right side. Also, the pressure at the stenosis was lower than that at both sides, while the velocity is faster, which satisfied Bernoulli's principle. And this is the result in Y-type vessels. We can see the velocity is larger in vessels with small radius, and the pressure on the inlet is larger than outlet. Besides, we controlled the injection dose of contrast media to observe the effectiveness and robustness of the proposed method under different conditions. Keeping the injection rate unchanged, we injected 200, 400, and 600 contrast media particles into blood particles respectively, corresponding to specific doses of contrast media, and recorded the diffusion situation at specific time, as shown in the figure. As can be seen, at the same time, the contrast media arrived at the same position, but the shade was different, indicating the different injection dose. We also kept the injection volume unchanged and changed the injection speed. We injected the contrast media at different velocity and recorded the diffusion at specific time. It can be seen that the contrast media in the column C with higher injection speed reached a more advanced position at the same time. We also compared our method to Huang's method. We conducted experiments in two representative vessels with diameters of 4 mm and 1.4 mm respectively. The first line A is Huang's results, and the second line B is ours. As can be seen from the figure, our method had smoother results, especially in capillary vessels, which indicated that the simulation results of our method is more accurate without particle artifacts. In ablation experiment, we discarded the density contribution of the vascular boundary, and the particles in the vessel were free from any constraints and scattered around without considering boundary conditions. Moreover, to better understand the impact of our improved two-phase mixture model, we also conducted ablation experiments on the Y-type bifurcated model about whether vascular viscous force was considered. The first line showed the result without vascular viscous force, and the second line showed our results. It can be seen that the pressure and velocity results became more stable after the term is added, and the velocity of fluid particles near the boundary was lower than that of near the centerline, which was more consistent with the actual situation. That's all of our presentation. Thank you so much for your attention.